Hello and welcome back. So what we're going to do in this video is very quickly do a review of what we did in the last video, at the end of the last video, and then we'll go on and talk a little bit more about reasoning with quantifiers. And then finally, I'm going to end off this section of the video by talking about some basic proof strategies. So first, let's go back and review multiple quantifiers for 1 second. So what I said was when we have multiple quantifiers, there are different situations where we can say that switching the quantifiers and switching the variables do not matter. And those are the cases where we have the same quantifier. So if we have for all x for all y, it's the same as saying for all y for all x. This should actually say y and x here. So switching the order of the quantifiers or the variables do not matter. And it's true when every pair of x and y is true of p of x. Okay. It is false when x and y, there's a pair x and y that makes p of xy false. Now, similarly, with the existence, if we say exist x, exist y, it's basically shortened to say there exists an x and y, right? A pair x and y, such that p of xy is true. So when is it true? I find one pair of x and y, so that p of xy is true. But how do we show it's false? We have to show somehow that every single pair of xy's will come out to be false. So I hope those are pretty straightforward. Those are just extensions from the basic quantifiers that we talked about before. So the harder parts are the ones that are that are mixed. So meaning that we have a for all and then an existence, or vice versa. So let's take a look at this one first. If we have a for all x exists y, p of x, it means that for every x, every single x, there has to be a y that goes with it so that p of xy is true. Okay, so I'll say that again. For every x, if there's a y that goes with it that makes p of xy true, then this is true. But when is it false? If there's even one x that doesn't have a y, then it's false. Okay, if there's even one x that doesn't have a y, then it's false. Okay, on the other hand, what about existence x for all y? So if we say exists x for all y, p of xy, that means it's true when there's one x. So you have to figure out what that x is. If there's one x, that it doesn't matter what y is, p of xy will be true. Okay, so find that one x, that it doesn't matter what y is, it will p of xy will always be true. So that statement will be true. But it's false when for every x there is a y such that p of xy is false. Okay, so that means there is no such x. There is no such x that every single y makes it true. Okay. All right, so do practice those questions that I've posted in the textbook. Those will really help you to analyze these types of questions and be in the habit of just saying it out loud. Like this statement is read as whatever, whatever, and that is going to help you with the logic to analyze whether it's true or false, and also to explain whether your statement is true or false. Now, I should add one last thing here, which is uh, I know we've looked at instances of multiple quantifiers where we only had two quantifiers, like a for all and exist. But understand that we can chain as many of them as we want. So typically in this course, you will see about two, maybe three at the most. But know that we can chain multiple quantifiers if we have that many variables, right? So for example, if we had a statement involving four variables, then we might have four quantifiers that go in front of it. And the logic, the way that we would analyze it is exactly the same as what we've done so far in this course. All right, so let's move on. Now, I want to start off this video by doing a little bit kind of a fun thing with logic. So let's say you go to an island, okay, and there's only two people on the island, and these two people are telling you things about themselves. Okay, so you meet two people. The first person says, exactly one of us is always lying. Okay, so exactly one of us is always lying. So lying means that they are falsifying what they say. And the other person says, at least one of us is always truthful. So at least one of us is always telling the truth. Now, this is what they say. Now, your goal here is to find out who is lying and who is telling the truth. So let's label this person A and this person B. Okay, so we have person A and person B, and they have things that they say corresponding to, correspondingly. So we want to figure out which one is lying, which one is telling the truth. So obviously, there are four answers here. Either they're both lying, okay, so they're both lying, or one of them is lying, one of them is telling the truth, which is two different cases. And then finally, the other case is they're both telling the truth. Okay, so which one is it? Well, I guess you can say there's a fifth case where I don't have enough details, I don't have enough information to find out, but in fact, we do. Okay, so take a second. Maybe you can pause the video here to just to think about this problem. And in fact, the truth tables that we've talked about a couple of videos ago will allow us to be able to figure this out. All right. So the first thing we'll do is I'm going to assign a variable. I'll call it small a. Okay. So small a is that person A is truthful. Okay. So person A is telling the truth, and B is the statement that B is truthful. So B is telling the truth. All right. So I'm going to figure out these instances here. So I have A and B. So A and B are truthful. So there are four cases. Okay. So once again, you can see that this corresponds to the four cases that I just said. They can both be lying. One of them is telling the truth, one of them is lying, or they're both telling the truth. So for each of these, I'm going to determine whether each of them is telling the truth. Okay, so here is so what A says is true. Okay, so I'm going to put what A says is true, and then here I'm going to say what B says is true. Okay, so I'm going to analyze exactly what they said based on each one of these variations, each one of these rows. Okay, so let's take a look at the first row. The first row is where A and B are both lying. Okay, so A and B are both lying. So is it representative of what A says? So A said exactly one of us is always lying. So is it exactly one of us is always lying? Well, no, not in this case because they're both lying, right? So it must be what A says is false. Okay, so what A says is false. So maybe if you're having trouble understanding this, I won't put this true here. What A says is dot dot dot, okay, and what B says is dot dot dot. But really, it's the same thing as what I just put here. So in this case, if they're both lying, right? A said exactly one of us is always lying, then what A says is false, right? What A says is falsified. Okay, but what about this second case? So A is lying, but B is telling the truth. So is it true that A, exactly one of us is always lying? Yes, what they're saying is true. And in this case, yes, what A is saying is true. Okay, what about the last case? Well, again, A is saying exactly one of us is always lying. That is false in this case. Okay, so take a second just to convince yourself that this represents what A is telling us. Okay, what is B telling us? B is telling us at least one of us is always truthful. So, when are the cases when B is actually truthful? Well, B is telling the truth in these three cases because he said at least one of us is always truthful. So, the only case is 0 here. All right, so now you may recognize this table as being the exclusive OR and the OR, respectively, but that's not the answer. The answer here is which case is possible. Okay, so which is it? Is it that they're both lying? Is it one of them's telling truth, one of them is lying, or they're both truthful? So the way that we can find this out is we analyze each one of the rows. This is what a good truth table or a proper truth table is going to tell us about the situation. So let's start with the bottom case. Okay, the bottom case, we are assuming that both A and B are telling the truth. Okay, we're saying that A is truthful and B is truthful. But what A said happened to be false. So can that happen? Can A be a truthful person, but what they say is false? So no, this cannot happen. So right now, I'm just going to say this case cannot happen. It cannot be the case that they're both telling the truth at the same time. That's not possible. Okay, so I'll explain that one more time. A and B are both telling the truth, but what A says is false. That can never happen, right? So that last case can never happen. What about the second to last case? Okay, the second to last case, we assumed A is telling the truth, but B is lying. But if B is lying and what they say is truthful, that can never happen either. So that's also crossed out. Now you could probably guess which case it is. So here, what about this case? Well, A is lying, but what they said is the truth. So no, this case can't happen either. What about the first case? Well, the first case is we assume that both A and B are lying, but and what A says is false and what B says is false. Can that happen? And the answer is yes. So this is our case. So ultimately, what is the answer here? The answer is that they are both lying. So I hope you are able to logically deduce that, but we can use a truth table to be able to figure this out. Okay, so this is a kind of a fun activity. Hopefully you're able to see kind of a usefulness of the truth tables. All right, so let's get back to today's stuff. So, at the beginning of today, what I want to do is talk a little bit more about how the quantifiers work. Now, I just want to do a very quick review of what we talked about in terms of connectives in the last class. So, let's pretend that I have an open statement called P and I have an open statement called Q. So, if I wanted to say all P are Q, okay, so all P are Q, then the way that we would translate this is for all x, right? P of x implies Q of x. Now, this is something that we have to remember. If you don't remember why it's an implies, go back and watch the previous video, right? But in short, because we have all, that this is a law, this is a rule. So there's going to be an implies. And on the other hand, if we had some PRQ, this is an exist x, P of x, and Q of x. Okay, so we have some PRQ. So again, if you don't remember why this is an and, go back and watch the previous video, but this is one case, right? So this is talking about one particular case. All right, so now let's think of a different form. What if I said I want the translation no PRQ? Okay, no PRQ. How do we translate no PRQ? In fact, let's do an example here. No pigs can fly. Okay, and in fact, let's say that our P of x is that x is a pig, and that Q of x is that x can fly. And I'm going to assume here the universe of animals. Okay, so universe of x is animals. So how do we translate this this statement? Well, the first thing is that we have to understand, or we have to ask ourselves: is this an all statement or is this a sum statement? Now, I think the easier way to think about this is that it's an all statement, right? It says something about all, but it is saying something in the negative sense. So we know that if this is an all statement, that it's going to be something like this. It's going to start with a for all, okay? And there's going to be a P in here, and there's going to be a Q in here. Okay, we know this. Okay, so the question is, what is implying what? Because for all, again, as we said, whenever we see a for all, there's going to be an implies. Okay, so the easy answer here is that we can say if you're a pig, then you cannot fly. Okay, now let's just read this and make sure that we understand the logic that is happening here. If I say no pigs can fly, then that means every animal, for every animal that's out there, if you are a pig, then you cannot fly. Okay, so again, verify, make sure you understand the logic that this is the same logic as no pigs can fly. Now, is there another way to write this? And I think there is. We can do something like for all, and we can say, if you can fly, then you are not a pig. Okay, for all animals X. If X can fly, then X is not a pig. Now, both of these are identical logics, and I want you to see why, because they are essentially contrapositives of each other. Remember what contrapositive is? P implies Q is the same as not Q implies not P. So verify that these are in fact contrapositives of each other, and they're saying exactly the same statement, exactly the same logic. Now there is another way that we can that we can write this, and that is, oh, by the way, we're going to do proofs in a little bit. If we're ever doing a proof with no PRQ, if we're trying to do a proof with no PRQ, this is probably the way to translate it. Okay, but there is actually another way that we can translate this statement. So if I apply the implication reduction law, I will get something like not P or, and then this is the same, right? So remember, P implies Q is not P or Q, right? This just happens to be not Q here. Now I'm going to pull this negation outside of the bracket, which makes this or an and. So I'm going to do P and Q of X, and there's going to be a negation in this bracket. But if I pull this negation even past the quantifier, even past the for all quantifier, this for all has to become an exist. Okay, so remember that law from last time. So this is going to be a not exist X. Okay, so just verify that this was from De Morgan's law that I got this answer. Now, if we read this again, this is saying there is no such animal. So there doesn't exist an animal that is a pig and can fly. Okay, so there's no animal that is a pig and can fly. So again, that's the same logic as saying no pigs can fly. But again, I stress that when we do a proof later on, that leaving it in the form of for all is probably better. It's better for our proof. Okay, so I mentioned proofs earlier. So let's talk a little bit about what are some strategies or what are some rules in order to prove quantified forms. So whenever we have an argument that involves quantified form, we need to apply some rules here. So there's two rules I want to stress here, which is called a universal instantiation and generalization, and existential instantiation and generalization. Now, these rules are actually quite simple. The first rule says that for all x, p of x is the same as saying p of c for any c in the universe. Okay, so P of C for any C in the universe. Now, these two things are just logically equal to each other. It just so happens that when we instantiate, we're going from left to right. Okay, when we instantiate, we're going from left to right, and when we generalize, we're going from right back to left. So anytime we do a proof, involving quantifiers, we have to use this universal instantiation and generalization in order to use the laws that we know from before. The reason is because the laws that we know from before, like modus ponens, modus tollens, all of those laws involve one statement. Okay, so if I make a statement like for all x p of x, I'm really making a statement on many statements. Remember, it's a bunch of ands that I'm putting together. But p of c is one statement. Okay, so if C is representative of the universe, I can simply write P of C, and that represents one statement. So I know it's something very small, but in order for us to properly represent a proof, we have to do this part. Now, the same thing goes for existential. So if I say existential x, P of x, this is logically equal to P of C for some C in the universe. And again, to instantiate, we go left to right, and then to generalize, we go from right to left. So we should keep these in mind because these are laws that we're going to work with, for the different proofs that we're going to make. But first, let's start off with a rather simple proof. All right, so I'm going to label this 314 here. So let's say I give you the argument for all x, p of x implies q of x. For all x, Q of x implies R of x. And therefore, for all x, P of x implies R of x. Okay, now if you remember the inference laws from last time from last video, you may remember this as syllogism, right? Because we said P implies Q, Q implies R, therefore P implies R. That was syllogism. However, this is not syllogism because it does involve the quantifiers. It's actually a bunch of rules that are a bunch of statements that are put together. So what we first have to do is apply the universal instantiation law. So for number 1 and number 2, these are in fact premises. And if I want to show the conclusion to be false, I'm going to have to say this implies number 3, and number 3 is P of C implies Q of C for any C. And we have to make this step or else the proof is not going to work. Number 4, similarly, we can say Q of C implies R of C, again for any C in the universe. And now we can continue our proof. Well, this proof is just really one line because now when we have P of C and Q of C and R of C, those represent one statement. And now we can apply syllogism law and we can say P of C implies R of C through syllogism of number 3 and number 4. So at this point, we know that C represents the universe, represents anything in the universe. And therefore, number 6, we can now say for all x, P of x implies R of x. And this was using the universal generalization law. Okay, so let me just go through that one more time. In step 3 and step 4, we were using the universal general instantiation or specification law. We turned for all into a statement involving just C, which is one statement. Then we can apply the laws. And when we get to the conclusion, we have to make one last step, which is to generalize, to do a universal generalization back to the conclusion. So now we can claim that this is valid. Okay, so just one extra step whenever we work with quantifiers in order to make this proof. Now, earlier I did mention existential quantifiers, but existential quantifiers are usually not used in this type of proof. So as I said before, when we're translating and we're trying to do a proof with quantifiers, it's probably best to turn it into a for all statement. Okay, so it's best to turn it into for all statement. Now, is there any use for instantiation, existential instantiation or existential generalization? Yes, there is. And we're going to talk about that in our next section. Okay, so in the section on number theory, we're going to get back to that and we're going to take a look at some uses for existential instantiation. Okay, let's do one more example here. Oh, I should probably make a new slide. Let's go to a white screen here. And let's do one more example. We'll call it 315. And I want to do one more proof. Now, this proof is going to be a little bit more challenging because I'm going to teach you a new technique. So let's say I have something like for all x, P of x, or Q of x. And for all x, not P of x, and Q of x implies R of x. There's a bracket here. And therefore, for all x, not R of x implies P of x. Okay, now I say this proof is a little bit harder because if you try to use the law, so let's just begin and then I'll tell you what problems we actually run into. So we have number 1 and number 2, which are premises. So as I said in the previous slide, we should change this into instantiation. So we have P of C or Q of C, and then we have not P of C and Q of C implies R of C. So there should be a bracket here. And now our goal is to get to the conclusion where not R of C. So eventually, I want to get to the point where not R of C implies P of C. Now, once I get to this point, it's very simple to just go through a generalization back to our conclusion. However, it's really difficult in this case because there's no laws. Seemingly, there are no laws to get me there. Okay, but there is actually a trick that we can do. Now, notice that in the conclusion is an implies. Okay, so in the conclusion, there's an implies. And anytime you see an implies in the conclusion, we can do a trick or a shortcut. So the trick is that we have number 3 and number 4, right? Number 5, I'm going to add the left-hand side, sorry, the left-hand side of the conclusion. So notice there's an implies here. I'm going to add not R of C, and I'm going to label this as an added premise. Okay, so the purpose of this added premise is that I'm now going to assume that not R of C is true, and eventually, somewhere down here, I want to show that this causes P of C to be guaranteed to be true. Okay, so this part that I'm about to do is just as good as proving not R of C implies P of C. Okay, so let me repeat that. Because we have an implies, because we have this implication here, we can add the left-hand side of this implies as an added premise, and then show the right-hand side of this implies. And if I can do that, this is just as good as showing the implication itself. Okay, so this is just a trick. Just remember this. If we ever need to do a proof, and it has an implies as a conclusion, you can do this. You can always add the left-hand side and then show the right-hand side. Now, before I show you why this works, let's just do the proof itself. So now that I have not R of C, we have, well, let's pretend this bracket here is an X, right? So I have X implies R, so X implies R. So if I have not R, then I have not X, right? And that was called modus tollens of number 4 and number 5. So review, if you don't remember modus tollens, take a look at that video from before. I'm going to distribute the negation inside this bracket. And I'm going to get P of C or not Q of C. So I have two negations, and I have to turn this and into an or. And now we're pretty close because you can see that we have number 3 and we have number 7. Right? So you can probably guess here that P of C is going to be true, but we still have to go through the process. So number 8, I'm going to combine the two. So I'm going to say P of C or not Q of C and P of C or Q of C. So I'm going to and number 3 and number 7 together, and that was called the conjunction law. So the conjunction law of number 3 and number 7, I can add them together. Two things that are true, I can add them together, and it's still true. And now I can pull out the P of C. So I can distribute the P of C here. And then I have an and Q of C. So if you have not Q and Q, this will give you a false. So false or P of C is just going to give me P of C. Okay, so those are from the laws that we know from before. All right, so once again, from number 5 up to number 11, so those steps are what's proving that. So I can probably label this as number 12. Number 12, we can say not R of C implies P of C, and then we can say step number 13 is our generalization back to the conclusion. All right, so some of you might not be convinced. Why is it that whenever in our conclusion we have an implies that I can simply add the left-hand side and then show the right-hand side? So why is it that that's true? So let's see if I can prove this to you in logic, using logic. So so ultimately we say we have a bunch of premises, and then the conclusion is also an argument, right? So if the argument is true, then that means the premise being true guarantees the conclusion. right? So if the conclusion itself is an argument, then surely we can add it to part of our argument. So let me do another blank slide here. Well, let's unwhite the screen, and then I'm going to show you another white screen. So when we had, let's say P1, P2, all the way up to Pn, and then my conclusion was Q implies R. Okay, what I'm saying is this is equivalent, logically equivalent to the argument P1, P2, all the way up to Pn, Q, and then therefore R. Those two are equivalent operations. So let's take a look at why that is. Okay, so let's pretend, just for our sake, that this is P. Okay, this is the P1 and P2 and P all the way up to Pn is P. Okay, so if I have P implies Q implies R. Okay, so I have P implies Q implies R. So let's do a little bit of algebra here. I'm going to get not P or not Q or R. Now, since both of these are ors, I can move the bracket over. I can move the bracket like this. Okay, and that was called associative law. All right, so using the associative law, I can do this. And then now I can pull the negations out of the bracket. I'm going to get P and Q, right? And now I have P and Q implies R. So you see, not X or R gives me X implies R. So you see, this is this argument, and this argument down here is this argument. So you see, we've added Q to part of the premises, and then all we need to show is R as a conclusion. Okay, so now I hope you're convinced that these two ways of proving is exactly the same. It's exactly the same statement that we're proving. Okay. All right. So now let's end off this subsection by talking about different types of proofs. So there are three types of proofs that I want you to be aware of. Again, I'm going to leave existence proof to a little bit later in the course. But for now, let's talk about three basic types of proofs. The first one is called a direct proof. Indirect proof is the second type, and then a proof by contradiction is the third type. So all three of these strategies we're going to use throughout the course. So when I say this is a direct proof, just try to remember exactly what it is. Now, these proofs are all proving the form P implies Q. So once again, all of these are proving the form P implies Q. So just as a start, let's make some definitions. So if I have a number, let's call it n. N is even. Okay, if and only if. So this is a definition. Okay, so n is even if and only if n can be written as 2k, where k is an integer. Okay, so this is the this is the definition of an even number that we're going to go with throughout the course. Similarly, I'm going to call another one d, and d is odd. It's an odd number, if and only if. D can be written as 2k plus 1, or D can be written as 2k minus 1, where k is an integer, is a whole number. Okay, so now given that these are the definitions that we're going to work with, I'm going to make a statement. So the statement is that if n is odd, then n squared is odd. Okay, now this n is, don't get it mixed up with our definition. N is just some number, some whole number that we're working with. So if n is a whole number, or sorry, if n is an odd number, then n squared is also an odd number. Now understand this as p and q respectively, but to be a little bit more exact, what this statement is actually saying is for all p, right? So for all p of n, it implies q of n, right? So for all n, P of n implies Q of n. That's really what we're saying here. Now, I have really just shortened the statement to P implies Q, but understand in the background, this is what we're dealing with. So how do we make such a proof? Well, the easiest way is called a direct proof, which says assume P and show Q. Okay, assume P and show Q. So what do we assume? We assume P is true. So that means we assume that n is odd. So imagine that we're working on on the argument, and what's above the line is P, and then what's below the line is Q. It's just that now we have other tools to help us. So not only the laws of logic, but also the laws of inference, right? We saw both of those laws, but also we can use the laws of math, or we can use any other knowledge that we have in our brain, right? So that's how we make an argument. So not only with those laws, but anything that's true, we can apply to this proof. Okay, so from n is odd, how do we show step by step that n squared also needs to be odd? So I'm going to say that if n is odd, this implies that n is in the form of 2k plus 1, where k is an integer. Now, this is true because it's a definition, right? Because we know this as a definition, so we can say this implies. Okay, what else? Well, this also implies that n squared is 2k plus 1 squared. And 2k plus 1 squared, if we work out the FOIL, is 4k squared plus 4k plus 1. Okay, so that statement, that third statement, is also true. What else is true? Well, 4k squared plus 4k can also be written as follows. So 4k squared can be written as 2k squared plus 2k plus 1. Now notice I factored out a 2 out of here, right? But also we can claim that because k is an integer, that this is also an integer. This is an integer because k is an integer. Okay, so now what can we say at this point? We can then say n squared is odd. And this is our statement Q. Okay, so notice that we started with P, we assume P is true, and then one direction, all the way down to where Q has to be true as well. Okay, so this is a direct proof. So anytime we say we're going to do a direct proof, we're going to figure out, first of all, what is the implication, right? What's the implication? We're going to assume that the implication, the premise is true, the P is true, and then through logic or through inference or through math or through anything else that we know, we're going to show that Q also has to be true. And once we're there, we're done. All right, we're done with this proof. Okay. So try to keep this strategy in mind. Again, there are a few practice questions that I'm going to be posting for this. Okay, but let's take a look at the second case. So this is called direct proof. Okay, just so you know. The second one is called an indirect proof. So again, we are trying to prove P implies Q, but this time we want to prove it indirectly. So let's say I have another statement. If n squared is odd, then n is odd. Okay, and again, we have a P and we have a Q. So again, we have a P implies Q, but this time, in order to do an indirect proof, we have to show not Q. So we have to assume not Q first of all, and then show not P. So essentially, we are showing the contrapositive of this rule, right? Showing the contrapositive of this rule. So what is not Q? Well, not Q is n is not odd. So if n is not odd, then that means n is even. So I probably should have mentioned that before. Every integer, it's either odd or it's even. It doesn't cross over, and it must be one or the other. So if n is not odd, then n must be even. So if n is even, what can we say? Well, n is equal to 2k, where k is an integer. So again, using the definition that we had in the previous slide. And then what can we say now about n squared? So n squared is equal to 2k squared, which is equal to 2 times 2k squared. And once again, very similar to the last example that we did, we can claim that this is nothing more than an integer, right? Because if k is an integer, then k squared is an integer, and 2 times an integer is always an integer, right? So we can claim that this is an integer, and we can say that therefore n squared is even. And therefore, we have the statement not p. So this is a indirect proof. All right, so I hope you understand the process. This is a simpler proof, but this technique we're going to use throughout the sections on number theory and everything like that. But for now, what I want you to see is that uh, is that there are two directions that we can show, right? We can use a direct direction or we can use an indirect direction. And you might be asking which one do I use, right? So if you just say prove this, which one should I use? Now the short answer is typically I will tell you use a direct proof or use an indirect proof, but in the case that I don't, it it will be that one is going to be easier than another. Okay, one will be easier than another. Here's another case. Now, notice in the last two examples that we did, right? In the last example, we showed that if n is odd, then n squared is odd, right? So we proved this. In this example, we showed that if n squared is odd, then n is odd. So notice that we actually proved both directions of this implication. We showed that n squared is odd implies n squared is odd. We also did the opposite direction. N squared is odd implies n is odd. So we can actually, through the last two examples, okay, so the last two examples showed that n is odd biconditional. N squared is odd. So this theorem actually went both ways, right? So what that tells you is that anytime you see, and by the way, how do we read a biconditional? It's if and only if. So essentially what we proved in the last two examples that n is odd if and only if n squared is odd. So anytime you see a proof, like I want to prove this if and only if this, then essentially I need to go two directions. I need to do both directions. I need to go direction in the forward direction and also in the backwards direction. So it's two separate proofs. And usually one direction is direct and the other has to be indirect. And one will be easier than another, right? So for each of those proofs, it should it should lend itself to one type of proof or another. All right. So we've talked about direct proof and we've talked about indirect proof. We'll talk about one last one, which is called the proof by contradiction. Okay. So again, let's assume that we want to prove P implies Q. Okay. We want to make the proof P implies Q. Now, before we talk about proof by contradiction, I want to say that proof by contradiction, at least this concept, works not only for implication, but for any type of proof. Okay, for any type of proof, you can use a proof by contradiction. So whether the statement, even if the statement is not and implies, we can use a proof by contradiction. And how it works is that first we assume the statement to be false. Okay, we first assume the statement to be false, and we show that this cannot happen. Okay, now in the case of an implication, how do I assume an implication is false? Well, I have to assume that P is true while Q is not. Okay, so P is true while Q is not. I have to assume those two things. Okay, and what I want to derive is a contradiction. What's a contradiction? It's a false. I have to derive the fact that this cannot happen, right? This case cannot happen. So another example, if 3n plus 2 is odd, then n is odd. All right. So again, we have a P implies Q, but again, realistically, it's saying for all, right? It's for all n, P of n implies Q of n, right? But we'll shorten this to P implies Q. So if we were to do this using a proof by contradiction, we would then assume P and assume not Q. Okay, so P says 3n plus 2 is odd, and not Q says n is even. So the question is, can these two things coexist? Can these two things happen at the same time? So our goal here, if this was a true statement, then our goal is to derive the fact that this could never happen. Okay, so let's see if we can do that. So from the premises that we have, now here we have two premises. From these two premises, since n is even, I can write n is equal to 2k, where k is an integer. Okay, and pretty similar to what we did in the last two examples, I can then write 3n plus 2 is 3 2k plus 2. Okay, now at this point, I want you to notice that the reason why I put n is even is because originally the statement was n is odd, right? So not q is the opposite of that. All right, so this I can write as 2 times 3k plus 1, which again, we can make an argument that this is an integer. And so this is a form of a even number. So what we can conclude from this is 3n plus 2 is even. Okay. Now notice that every statement I wrote down at this point is assumed to be true, right? All of these things that I wrote down are assumed to be true. In particular, I have this statement and I also have this statement. So I have those two starred statements and they're both assumed to be true. I can AND them together. I can say 3n plus 2 is even and odd. And can this happen? The answer is no, we can't. We can't have a number which is even and odd, and this derives a contradiction. And at this point, we're done. So the funny thing about contradiction is that your last step is always false. Okay, once we derive the false, we're done. Okay. Now, I hope you can understand the mathematics that are happening at each stage of this proof. But what I want to very quickly show you is, why does this proof work? Okay, so let's say we make a statement, and again, doesn't have to be an imply statement. So I make just some statement. So the argument is, let's pretend that this statement is false. Okay, let's assume that this statement is false, which we did in the first two lines here. This statement can never be false, and therefore it must be true. Okay, so this is actually very similar to when we did the inference proofs and we tried to find an invalid case, and there's no invalid case, it must be valid, right? So assume that the conclusion is false and the premise is true. It could never happen like that. Therefore, the whole argument must be true. Okay, so that is the idea of the proof by contradiction. Okay, so this is how we argue. Let's assume I'm wrong. I cannot be wrong. This is why I cannot be wrong. And therefore, I'm right. Okay, so that's kind of an argument form. And proof by contradiction is actually very powerful. It's a technique that we're going to use over and over in this course. So try to remember the idea. Okay, so number one, assume the opposite, assume false, show contradiction, and therefore your original statement must be true. Okay, so I think this ends off this section. So I will see you in the next video.